Yeah, so welcome everybody. I'd love to introduce Gautam Prasad from Google Research, who's been, mapping populations across the world from like the electronic data we have available, like the new set of eyes we have on how people behave. So welcome, Gautam.
Yeah, thank you for the opportunity to speak here. And so I'll give an overview of the Population Dynamics Foundation model. This is a project we've been working on for a couple of years. I'll give some kind of background for how Google got to this point, kind of the different research milestones that brought us to try to work on foundation models. And so back in 2011, there's this really important research paper from Hao Darian and Han Young about using Google Trends to map out tons of economic things and having really state-of-the-art results doing that. And that gave us a lot of confidence that Google search trends could be really useful for modeling really useful things like disease or economic things. And the next iteration of this was flu trends and trying to map that out with some representation of search data. And this proved to be really powerful for understanding the progress and kind of forecasting these types of communicable diseases. But one of the big issues that happened with this is the representation of search data evolves over time. Like the way people are using search, the way other things like news influences it. And so that feature representation of this type of search signal needs to be updated relatively frequently. And so one of the big things that happened is after this initial prototype, the team moved on to something else. This old version of search that worked really well initially for flu became outdated. And there was a bunch of analysis showing that it wasn't as useful anymore for predicting flu trends. And the big thing here is that initial representation of search data, it's very customized for flu for that particular time point. And it did work for a little while, but it needed to be refreshed to be able to track flu effectively. And so one way we can tackle this is we introduce this new data set called symptom search data set, and this tracks 300 different symptoms. And it's public, you can download it, it's publicly available. It's at it's available all over the world. And this became a really important signal for COVID and flu tracking around the world. And the nice aspect here is that we are able to refresh this signal relatively frequently so that people like this team in the UK were able to use it for flu and COVID tracking every 2 weeks. And this is really nice because it provides an index into 300 different symptoms that affect people around the world. You can feed it into an existing model, and it provides one step closer to being widely applicable to a bunch of diseases and things that might affect people's health. But even then, we wanted to try to broaden it even further so we can apply it to a much wider swath outside of health to commercial applications, socioeconomic ones, environmental ones, and also include health. And to do this, we wanted to like broaden the types of attributes we're tracking about people. And so part of this is we want to understand what people are searching for, what they're thinking about, like the search signal. We also understand some version of mobility of how people are interacting with their environment and their city, get a sense of environmental factors like weather and air quality, and also just how the city's structured, like where are roads, like where are the frequent places people are going, what types of businesses are available, what do they say about the types of jobs people have, the types of social interactions they have. And we wanted to put all of this into like one easy to use model that people could apply to all these types of problems. And that's one of the big things that's been happening with machine learning lately is people are building these big foundation models. And the whole goal here is that they provide a general purpose start for tackling all these downstream modeling problems. And so like to make all of this very concrete, I'll start with an example for how you can apply a foundation model for a specific problem, and then I'll go into the details of how foundation models work for us and how we built it. And so in this example, we're trying to understand diabetes prevalence at a resolution finer than what the census gives us or whatever a state or counties provide. And so we're looking at New York State in the United States. And in that state, we can say we have county level diabetes prevalence rates. And we can compute an embedding or a set of features from our foundation model at each of those counties. And this is using some model we've trained on a bunch of Google and publicly available data sets. And then what we can do is train a very simple downstream model that connects those embeddings or the features with the county level diabetes prevalence. And this model could be a neural network, it could be decision trees, or like it can even be linear regression. And the whole point here is that downstream model can be relatively simple, but it allows the heavy lifting of the modeling to be done when it pushes all of that information into the embedding or the features. And the result of this is we get, let's say, some linear model that tells you, given an embedding or features at a county, it can tell you what the diabetes prevalence of that county is, because we have that ground truth there. And then we can go to a finer resolution, so zip code level, which is smaller than county spatially, and compute the PDFM or the features at every single zip code. And then we can apply that same county level model with those zip code features to super resolve or get super resolution of diabetes prevalence. And then we've tested this with cross-validation, and we've shown that works really effectively when we want to super resolve something. And the whole value here is that embedding or features are available at a finer resolution. So we understand the mapping between search, maps, weather, air quality, and diabetes prevalence. If we can generate those features at finer resolutions, then we can easily apply that same pattern there. And that's why it's really effective. And so this is a broad overview for how the population dynamics foundation model works. What we've done is taken aggregated search trends. I'll go into more details on that. Representation of Google Maps, some summary of point-wise mobility, like the place visits to each of those locations. And then we have a set of 30 or so attributes related to weather and air quality. And this is all fed into a graph neural network. And we use like self-supervised learning to try to extract all of that information into a very compact representation around 300. Like you can think about it as like a feature vector of 300 at every single location that you care about. And our initial study was focused on the US, and we were looking at counties and zip codes. So you can think about it as every county and zip code has a set of features that are derived from this model. And then the second stage is once we are able to generate these features, we can feed it into any downstream model architecture we care about. And so you can think about linear regression or a simple multi-layer perceptron network. And the way that this works is we need a small amount of ground truth. And so, for example, in that diabetes prevalence example, we could apply it into many different scenarios. These include interpolation, so you could think of the whole US and little parts of it missing, and we can train the model to fill in those gaps of maybe counties or zip codes missing. Extrapolation is another setup where whole states might be missing, and we have to try to recreate that kind of census data there. Super resolution, which I talked about before, is where we go to a finer resolution. And then in combination with another model, we can do nowcasting or forecasting, where we're trying to pivot very near-term statistics about geospatial statistics about a place, or longer-term forecasting about it. And what powers this is, in these instances, we take our embeddings or our features, and we apply this very simple downstream model to kind of extrapolate or interpolate it across these larger places.
So question at this point, you say graph neural network. So then intuitively, what are the nodes and edges and kind of why this structure? What bias are you incorporating?
I can jump to, okay, well.
Oh, no, you can go back to if you have slides for that.
But maybe I'll tackle that. So in this case, the nodes are counties or zip codes. And then the edges we used are the spatial proximity between those counties and zip codes and like their relationship, if there's an overlap, and also the pairwise correlation in the search data between, you could think between any two nodes. So like a county in California versus one in New York, like what would be the search similarity there? And this allows both like the local patterns of connectivity, but also like longer term, larger scale connections across the country, which like might not be initially intuitive, like because they're not close to each other especially, but they might have similar demographics or industries or weather patterns that we're trying to capture in those relationships.
And the intuition sounds like it's a similarity matrix. It's not an information propagation. Oh, no, it is. The intuition is it that they're similar so you can correlate, or that they causally affect each other, so information about one eventually propagates or affects information about the other?
Yeah, and I'll go into the architecture too, but like the information can propagate.
Got it.
We can do like a couple cycles of information propagating through the nodes, and you can think of it as each node has like their own little neural network in practice that is gathering information about the adjoining nodes that are connected through these edges. And that is eventually, like, so the embedding that we in the end pull out from a node is actually encompassing a lot more than just that single node's information. It is like feeding in information from adjacent nodes.
Got it. Thank you.
Yeah, I'll dive in a bit more on each of the data sets that we fed into it. So the search trends data is the top 1,000 search queries across the US. And we've done a little thing, a few different post-processing things to balance it out to make sure that a state that's really populous has some, like, let's say California or Texas specific search queries that aren't available for the rest of the country. So we try to balance it out so that the search queries are represented at a certain number of counties or zip codes around the country. And in practice, all we're doing is taking the counts across this fixed number of top 1,000 search queries. We actually throw away the text of the search query and only look at like this histogram of counts. And I think the big insight or discovery we found here is that if we take the most popular search trends and put them in a downstream model, they're very effective at even capturing very niche or specific goals. So for example, that diabetes trends, that diabetes prevalence example before we would have used a symptom search data set where we mapped out all these symptoms. We might take a subset of those that are related to diabetes and try to understand a model. But we found that somehow the top most popular search trends that might not have anything to do with diabetes or health actually is able to map some representation of human behavior to understand health really well. And this is really nice because it allows us to have a lot of spatial coverage, because these top search queries are something that most humans start looking for. And it allows us to preserve a lot of privacy too, because in most counties or states, there's a ton of searches related to the top 1,000.
Got it. So this is interesting. I mean, first of all, it's not the most popular. It's the most median popular, like by count, or what's called spatial distribution, which is neat. And I'm a little surprised that this works. I mean, I guess, do you have an intuition for why? Like, what about these things that is so task specific?
I think like there must be some indirect relationship for, let's say the top search queries were like TV shows and places to eat. And so if you look at that pattern for 1,000 things, maybe you understand, oh, this person has a cold because they're like eating more or they're watching TV less, or you get a sense of like, oh, what is their, like the types of professions that they do and like how much time can they spend on leisure activities. So I don't think it's like a clear direct relationship people want oftentimes, but it's sort of indirect. You kind of understand like what are the things driving people and what's important to them. And maybe you can like do the hops to understand like, oh, this is how you're affecting people's lives. But yeah, that's kind of my intuition here. And then maybe the second thing is if you go to like Google search trends and you try to pick out something very specific, like the types of food people are eating, the signal might be just so low there and there's a lot of noise. And so if you go to the very top search queries, it could be like, oh, there's a ton of signal compared to noise. And it's also indirectly related, but still it's such a strong signal that we can kind of model it using some like downstream model to try to extract like the human behavior from it.
Yeah, that's helpful. And then maybe one more thing. This is a non-neural algorithm, it's a median count spread thing. Would it make sense or be helpful to like train a model of all search trends to figure out which non-linear combination of search trends is a good embedding of just a signal, or do you think just the simple coverage thing is more appropriate?
Oh, you're saying look at the subset of things that are driving it?
Well, I think right now you just take a subset based on a solid heuristic. And the obvious alternative is to make a neural embedding of just the trends, but not all of them. Have a neural net plot these things out on its own. And I'm not sure that's a constructive way of doing it.
Oh, there was a little bit. There's like another team at Google who actually published a paper where they put a broader set, they kind of embedded a broader set of
intuition, yeah.
And they had good results doing that. We tried a similar experiment, and in these initially, the top 1,000 seemed to be good enough. And maybe it's, yeah, maybe my intuition is just maybe it's throwing in so much more. Like you have to figure out how to weight them equally. Maybe it's like the number of search trends. I'm trying to remember. Maybe we did this. We did weight them by the number, like the sort of magnitude of the search trends. But then maybe it get, like my intuition is it just maybe at the long tail it just gets really, really noisy, and so it's just dumping a bunch of noise in it.
That's fair.
I think this is sort of an open research area. Like we could probably do it more effectively. And I intuitively, you want to, like, if you want to model something really specific, like maybe like home prices, you'd be like, oh, okay, maybe let's try to like figure out the most important things that are interpretable and everything. So that maybe there's a way to do that as well. I mean, the other aspect here is like we could maybe like broaden this to 5,000 instead of 1,000.
Easily, yeah.
The downstream models that like, even like once they're going into the graph neural network and there's some like downstream linear model, in some ways they are sort of indexing into a subset of the search trends in some way, but like it's probably not as interpretable at that point.
Right. Okay, awesome data. Thank you.
Yeah. We do a similar thing with maps where we take the top 1,000 or so most popular points of interest. So this could be like some broad category, like coffee shops in a zip code or county. And we rank them total. So whatever the most popular points of interest in the country, we look at the histogram of counts in zip codes and counties. And you can think of this as like another histogram, and we're throwing out the actual names of those points of interest or the categories of those points of interest. And this is meant to be a quick index into like what types of buildings, like the road density around counties and zip codes around the country. Another like very related signal is for each of those points of interest, we have a measure of the busyness or the place visits for each of those. This is so like how many people came to a coffee shop across like an entire month. And I'll also add one thing that I didn't mention before to be more specific, like the search data, and at least in our initial experiment, was from 1 month. More specifically in 2022, the maps and the busyness for our initial analysis was from 2024. And like at first, this disparity in time seems like it's going to be a huge problem, but well, like the results actually kind of work themselves out, and it wasn't an issue. And I think we did we did a little analysis where you could like time sync everything, and there is a benefit. But even with things off by different time points, it works pretty well. I'll also add, yeah, we have a team at Google that teams at Google that analyze weather and air quality, and so we have a bunch of statistics about precipitation and different types of air quality particulate measures, and we map them all into a vector of around 30 statistics, and we have those for an entire month across every zip code and county as well. And so like this is all the data that we have to begin with that's fed into our graph neural network. And this is the full architecture of the network. And like on the top right, you can see the exact counts for each of the features that we fed into it. The nodes are counties or zip codes. We look at the spatial like relationships between all of them. We also look at the correlation between, or the affinity between, search signals in each of those nodes. And so that's another weight for the edges. And then we use an approach called GraphSage to aggregate the features across that of all the nodes connected to like your target node, and we learn a neural network on top of that. And the end result of this you could think about is, at a node, you initially have this stack of features from search, maps, busyness, weather, air quality, but you also have like all the neighboring relationships. And so you take those edge weights, the features at each of the adjacent nodes, and you put them all together, and you learn this network that kind of looks at this neighborhood around to generate an output embedding. And the loss that we're trying to optimize is to recreate that input data in some form. And so we're like kind of, you can think of this as some version of an autoencoder where we're trying to recreate the input data in some way, but also trying to take into account the network effects. The other thing we designed here is that the embedding is split into 3 distinct parts. One is search trends, another is maps and busyness, and another is weather and air quality. And so each of those are separate components of this embedding. And when this is fed into a downstream analysis, it gives like a little bit of interpretability there, where you could pinpoint, is search trends driving your prediction, or is it really weather and air quality?
So when you're making this prediction, you're making sure to have a small hidden state, so the original state of a node is mostly gone. You have to compress it, right?
Yeah, exactly.
Autoencoder.
Yeah, and it's like it's almost like, is it like almost 3,000? Yeah, almost 3,000 features that go in, and then we end up with a vector that's around 330 in dimension.
Question. So the weather AQI and the maps, the busyness, these are more or less like quantitative features, whereas the search trends, you need to embed them. When you do the in your figure A or in your figure D, when you get the outputs for the embedding, in the embedding where you have the search trends, the maps and busyness, and the weather and AQI, what types of embeddings are those? As in, are they embeddings for the weather and AQI in some embedding space?
Yeah, well, and then, okay, so to your first point, they're all like quantitative. So like the search trends is basically a histogram over these like top 1,000 search queries. So you could think about it as for a specific zip code. This is like initially a list of 1,000 integers. Like we normalize it, but think of it as 1,000 integers. And the same with like maps and busyness. So they really have a very similar form. Weather and air quality probably have a lot of floating point numbers, but I mean, it's similar, like it's a vector of numbers. And then for this final embedding representation, you could sort of think about it in that you have this data for a neighborhood of nodes, and you have these edge weights that are like mapped to those neighboring data points, and then they're all fed into a few neural network layers. And then out of that, you can extract some representation. And that's the embedding.
So are you looking, so I think this goes back to something Greg said earlier. Are you looking for something like a best representation or a proxy where you're able to get a some function of all of these features to serve as a proxy for whatever quantity you want to model?
Yeah, well, we like, so in this representation, this, like, let's say we look at the search trends embedding, which is like the first chunk of like features outside of in this like green box here. We have a during training, we have a downstream model that will take that embedding and then try to recreate the input search data. And so like in this stage, that's all we care about. We're just trying to create the input data. And then the whole hope of this foundation model is that afterwards, if we throw it into a downstream model, it's able to like be a general purpose solution for doing like home prices, nighttime lights, like the rate of asthma. And that's like a hypothesis. Like at this point, like we're just saying we hope all this data helps with that, but we aren't directly like when we train this, we're not looking at any of those downstream things directly.
Oh, okay. Thank you.
Let me ask you about that. So it seems like a geospatial feature. Actually, nighttime lights is a fantastic example because it's a social geospatial feature. To what extent would it be useful to incorporate geospatial features like weather or things that obviously affect the community but are not in a different modality? Arguably, it's more of a satellite modality.
Oh, would it be better to incorporate that?
You start incorporating these things which are kind of geospatial, weather, kind of that modality into this graph formulation.
Yeah, and I mean, like another thing, like in our initial formulation here, we don't have it, but there's another foundation model called SatClip, which is based on satellite data, and we do join them together. But I mean, I think that's like a future direction for us too, is to throw in satellite data and remote sensing data to fill in gaps. And part of this is like when we extend this model in the US, like there are constraints where we can't include search trends for certain zip codes and counties because there's not enough population density, and we need to like adhere to different privacy constraints. And so one of the benefits of this whole graph neural network is in those instances, if we're trying to predict like economic statistics from, let's say, the like US Census, we don't have enough like search trends just in that node. And really that's when the power of this graph neural network comes into play, because it'll be like, oh, this neighborhood like looks similar to somewhere else where I actually have search trends, and then can hopefully fill in those gaps. And I think that like that's sort of like why this post-processing step is effective and useful, compared to just like taking a big vector of 3,000 things and feeding it into a model. But it also it also matters that like probably in the richest, like the places in the country that have the highest population density, it's probably not a big deal. But whenever we're like missing underlying signals, then we're sort of like being able to learn from places that look similar or related.
Got it. Neil, thank you very much.
Yeah. Okay, so I'll also, well, yeah, I think I went over before how we can do this downstream modeling process on the right. And maybe it's intuitive, like interpolation, extrapolation, and super resolution. But for forecasting, it gets a bit more complicated. And the way we were able to accomplish this is use this model from Google Research called TimesFM. And this is a transform-based model, and it generally lets you predict the future for any univariate time series. So like if you have the amount of like the home prices for the last 20 years for like a specific zip code, this will just let you predict this out in the future. And it's a really nice general purpose foundation model. But one of the things it doesn't do is incorporate geospatial reasoning. So it's not changing its prediction significantly if you're trying to predict the home prices in Texas versus Montana. And so the way that we're able to provide that reasoning capabilities is we learn an adapter model on top of TimesFM. And so what, in practice, what this means is we looked at, let's say, unemployment and poverty across the US for the last 20 years, and we can make a prediction at every single county or zip code for using TimesFM into the future. And then we can learn an adapter model that tries to fix the errors from this prediction and incorporate a prior or embedding at that specific zip code. So like the idea here is that we'll learn how to improve the forecast differently depending on the zip code in the country, because we have this very rich representation of the attributes of that zip code. And then we can apply this adapter model for doing any type of like future forecasting. And then, yeah, I'll dive into the results. And so the way,
let me ask you about that one. Because the existence of TimesFM is kind of magical to me, because as far as I can tell, it just takes a prefix of time series, no context, no alignment with Allen or anything, and just does something sensible, which seems fairly impossible, but it does a credible job. But that, my real question then is, I would have expected you to do it the other way around. First, bias the TimesFM embeddings and say, no, this is really the context I'm dealing with, predict. But you did it the other way around. You took the TimesFM embeddings and fixed those up. Why?
I think for us, it was just easier to start with an existing forecast and then figure out how we can like post-process it to fix it. And there, like, I think since our initial version, TimesFM did add an API, which we haven't tested yet, for adding the embeddings as like a covariate, which is more like predicting it, which that might be a more elegant way actually to do this in the future. But for us, it was more about like if we had a hypothesis that depending on where you are in the country and describing like the conditions there could assist in doing any type of forecast, that was sort of an easy setup for the modeling purposes, because then we're not even tackling forecasting at that point. We're just saying here's a set of numbers that we're trying to fix. And so we like in practice, our adapter network is just like could be like a simple multi-layer perceptron and with a fixed size. It doesn't have to be autoregressive or anything. So that was sort of like an easy way to test this out.
Got it. Well, that actually makes a lot of sense. You can do an easy experiment and learn.
Yeah.
Awesome.
And and it's like I think we're like hopefully in the next few months we have some experiments with their like covariate and see how that fares. But yeah, it's a really good model too. It's very hard to do better than what TimesFM is predicting, which is so to benchmark this, we looked at a bunch of census variables across health, socioeconomic, and environment. And we also used a platform called Earth Engine from Google, which aggregates a bunch of satellite and geospatial statistics. So that helps us look at like tree cover, or even they have things like nighttime lights, and we can map those all to zip codes and counties to validate the performance of our model across tasks like interpolation, extrapolation, super resolution forecasting. And for a lot of the census level statistics, there's another platform called Data Commons, which aggregates these sort of census statistics across the world and is a really great resources for being able to extract a specific type of metric that might affect humans' lives across like all of these like very broad categories. And we also compared our method to a bunch of existing techniques. So one is inverse distance weighting, which is sort of like a traditional technique where you try to extrapolate or interpolate some data you have without using any external features. This might have been like how you do it before foundation models or how you do it before you have any covariates or anything. We also looked at RBF and Kriging, but found that IDW performed the best when we tried to compare these more basic methods. We also compared to SatClip, which I mentioned before, and this is a foundation model that takes a couple years of satellite data, Sentinel-2 data, and maps it out into embedding. We looked at GeoClip, which is an embedding based on personal photography. So all of these photographs that people take are geotagged, and they create an embedding based on the content there. And that's similar to like a social media or search signal as well. And then the last one is like the version of PDFM here. And then here are some visualizations, like IDW is the first one about like it kind of maps neighborhoods together. This is what SatClip and GeoClip look like. And then on the top right is a broad comparison across, I'll go into more details, of these three categories of benchmarks. And we found in general, PDFM was able to have like pretty strong performance and state-of-the-art in most cases. Here's like a very fine-grained breakdown across interpolation, extrapolation, and super resolution tasks. And you can see like oftentimes when we break down the underlying signals for PDFM, we're typically able to achieve the best performance when we combine everything together. But there are instances like extrapolation where like tree cover and elevation are doing better with GeoClip, or super resolution where like elevation is best when you use like a really basic method. And maybe like all these population signals, it's harder to understand elevation by default from them. But in general, it works really well, and it's just general purpose. Like these are just simple downstream models. We experimented with gradient boosted decision trees as the downstream model, these simple neural networks, even linear regression, and they all perform pretty similarly, which is kind of nice because if someone isn't as familiar with ML, they can sort of try a few approaches that they're familiar with and hopefully get some decent results. And then on the bottom right is our forecasting comparison. And we looked at unemployment at the county level and poverty at the postal code level. And the setup is we try to compare the default TimesFM forecast with the ground truth. Then we compared it with ARIMA, which is a supervised version. It's not a foundation model. It's actually like trained to predict this. And then TimesFM plus the PDFM embeddings through this adapter model. And we found like we were able to achieve the best performance with this combination together. Yeah, here's some visualizations of what this looks like. If you were looking at diabetes prevalence interpolation, like you can see the actual on the top left, and then PDFM versus SatClip versus GeoClip, and kind of like gives insights into like the types of resolution that we're understanding with each of these models. And then here, yeah, here's another breakdown of results across diabetes, income, and elevation. So yeah, PDFM is able to extract a lot of really important information. And sometimes you can like see some of these models will either be too coarse or too much diversity in their predictions as well. Oh yeah. Here's like an interesting point. One really interesting experiment we did is we combined PDFM with SatClip. and so this makes like a lot of intuitive sense. You want to throw some remote sensing signals, especially in places where there might not be as much internet penetration, and the search signal is not strong. This could be really helpful. And so for a lot of examples, this really helps improve performance. Like you could look at free cover for interpolation, or I mean, even income level, it does move it a little bit. But there are instances like with extrapolation where the performance actually degrades. And it could be that it's relying too much on this like new sat clip signal. So that's something we're trying to figure out. How do we combine these signals together? And it's not, I think initially we thought, let's just throw everything together in one model, but it actually takes a lot of work to get each additional signal to add value, to make sure like we're weighting it correctly and the architecture is adaptable to that. And I'll go through a few examples of how people have used PDFM, and like if you want to use it, how to go about doing that. So one example is this geospatial AI startup called Sust Global, and they have a product called Populous, and they're trying to predict AI insurance premium, or like predict insurance premiums. On the left is the architecture they're using. One interesting thing is for their models, they needed a smaller dimensionality, so they used PCA to further reduce from 330 dimensions to I think around 30 dimensions. And part of this is their downstream modeling did not have as high of a sample size. And so learning something on top of like 300 features just didn't make sense for them. But basically what they found is for analyzing premiums across the counties that they were looking at, PDFM like provided like a really strong input signal compared to the climate features that they were using. And so they embedded it into this new product for understanding statistics around insurance premiums. Another very recent analysis was done by Cardo, and this is like a cloud-based location intelligence platform. And they have this very specific feature set called Human Activity Index, which is like a handcrafted set of population, POIs, cell phone tower information, and they tried to see if they could predict that with this very general purpose foundation model, and they were able to account for around 90% of the variance with that. And they have this geospatial workflow that powered all of that connectivity. Another partner is Group M, which is a big ads client for Google, and they're using it as a way to help with understanding media performance insights and how to cater things for audio intelligence, and having this as sort of an index for understanding specific locations and using that as a prior. We're also partnering with Cooper Smith, and they're using versions of these embeddings in low resource environments for disease tracking, especially in places where there's just not a lot of existing data to help with this. And doing some experiments around HIV and malaria. And then, oh yeah, if you want to learn more, we did a UN AI for Good workshop, and I think it's very different from this talk in that we had this really great professor from University of Tennessee go through collabs or like Python notebooks to help understand how you could use the embeddings to model housing prices or nighttime lights. I'll also like plug that this is part of a suite of foundation models we have at Google, so you can check out this blog post to gain access and sign up to all of these foundation models. And we have like a GitHub repository with a bunch of code examples that you can play around with as well. Yeah, and that's all I had for the slides.
Well, yeah, fantastic. Yeah, thank you very much. So I do want to get at some of the mechanics, kind of the biases you are like explicitly putting into the model. One thing is that the graph structure. So one thing I didn't get, so normally graph neural nets have different types of edges and they propagate information across them all. It seems like you only have one. So it seems like ultimately just propagating, it's kind of a nearest neighbor model where you just keep pinging information from nearest neighbors and you're incorporating kind of how far away they are. Is that the structural intuition?
And then we also have edges related to search similarity as well.
And they're separate, like you train separate weights for distance and search similarity edges.
The weights are based on the distance, or like the edge weights would be based on the similarity. And so both of those weights would go into the network when it's learning the final embedding. But we're not training like the network to generate new types of edge weights right now.
Right, but you have two types of edges, so two sets of weights for each type. Okay. The other thing is, I'm noticing this is an interpolation based intuition, where it's like whatever the nearest, well, I forget the name, the nearest neighbor one, the weighted nearest neighbor. But now, of course, it's the neural weighted nearest neighbor. But you don't have like causal features, and this is interesting to me because there's some things where, okay, this is not environment. I mean, I'm thinking in a corporate hierarchy, management and workers are very different things, but managers affect workers and workers affect managers, despite their heterogeneity. And Geospatial has an analog that different things are informing each other by causality.
Yeah, that's a really good point. We're not finding causality here. And then even the relationships with county and zip codes, like there's not we're not like saying that explicitly that the counties are like a different type of node as well. And so you're right, this is all just sort of like correlations and things between all the nodes. And maybe the other big thing is ideally we have some representation that at least gets close to causality in the temporal domain. And so we can have these embeddings go through time. And that's like something we're actively working on right now. And then maybe like the mobility signal becomes more important, the change in like weather across time becomes more important. And how do we represent that effectively? We're playing around with a few different graph neural network architectures to try to understand that better as well.
Yeah, it makes a lot of sense. And now in your super resolution stuff, you went you took an interesting approach where I want to make sure I summarize it correctly. You said, I'm going to take the embeddings for a county, and presumably that means you just aggregate all, like add up, average all the embedding values within that county, then predict the information you care about, or is it the diabetes, I think it was. And that model now goes from aggregated embeddings to diabetes. You apply that same model, applying to that model to zip code, such that they still add up to the county. Is that fair?
Oh, I don't think that constraint matters that they have to add. Well, are you saying that
you don't train for it.
The zip code embeddings need to add out to the counties?
Well, right. Like I'm thinking classic or a generalized super resolution has some of these things because metrics that are administratively collected, I mean, crop yields are administratively collected, whereas the underlying data is like field, right? Same template. So I'm trying to compare how that community does it, how you do it.
The complication here is that the count, like let's say there was 10 zip codes in a county, the weight of each of those zip codes on some county level statistic might be very different depending on the population density there too. So like maybe it's not as simple as like in the image domain where we break something up into pieces. It's sort of like a more complex relationship between the two of them. So we have an experiment where we just take the zip code embeddings, like summarize them to the county and then model things. And we have other ones where we like actually have a separate node for the county and we generate features from that. And then in that case, the relationship between like the zip code embeddings that the county covers is probably like is not as clean. It might be some more complex relationship because you're weighting each of those zip codes in some weird way. Maybe there's like one zip code that everyone lives in and that is driving all of the performance.
Right. So now that's interesting because that's your super resolution approach. It's not that you're averaging or whatever, you're neuronally like having like training neural embedding from a bunch of these components that are conditional on population and whatnot, and that's a trainable function now, the combination.
Yeah, and I mean, I think the super resolution was like the hardest version, and especially I think there's like 3,000 counties in the U.S. And maybe 30,000-ish zip codes, and so when we were like evaluating super resolution, there's just so much less training data compared to like interpolation, where we actually are operating on this big like 30,000 point map across the US. So I mean, I think that's in general, it's a very difficult problem.
So let me ask a different application. I'm thinking, so like how variant stuff was like, I think labor trends based on search trends, which makes perfect sense. This is starting to get into much finer grained stuff. Like I give you an example of crop yields. Let's push on that one. How many, I don't know, toothbrushes might be produced or consumed in a given area, right? And getting a fine-grained spatially idea of an economy. How informative is like, how far can we get to that, do you think, based on the available information?
If we had like, let's say our goal was to predict toothbrush output at zip code level, if we had enough examples where we had that ground truth for a few zip codes, like I think we could get pretty close. And my intuition here is that for a zip code to produce toothbrushes, there's some kind of signature of the types of like factories. Is the city set up? Are cities within zip codes, or like, sorry, like are like neighborhoods set up within zip codes able like to do manufacturing, or like is this like a place where there's just like a bunch of software engineers, and hopefully we're able to index that, and we're like, oh, okay, like people are producing toothbrushes because like the streets look like this, the types of restaurants that toothbrush creators like to go to are there. That would be the hope in those scenarios.
Actually, hitting some yet another capability that you can theoretically develop. Where would I set up my toothbrush factory or my software center, right? Because it's core competencies of the people, the legislation, what kind of pollution laws there are. Like in the Bay Area, it's hard to put up any factory for gear pollution. Somewhere else it might be much easier because it's sparse population, right?
Yeah, I think that's like a really important use case, like the franchise use case, where you want to put like, oh, would an EV charger work here? Like it's worked really well in all these other places in the country, or would a coffee shop work here? Like what are other places it's worked well on? And I think that's a combination of many factors. Like it could also be like the weather. Is it cloudy here all the time? Like, do people want to drink coffee? Is the air quality like good or bad? Are people willing to walk to this coffee shop very often? Like what types of professions, like how many people are like visiting shops nearby? Like, is there going to be enough foot traffic for something to be successful? So I think that's actually like one of the like fundamentally like good use cases for something like this, to kind of like understand how people are operating in a place and give some kind of a model, like give some quantitative like feedback on like, oh, will this be successful?
Got it. Are there any other questions in the call?
Yeah. Thanks for the talk, Gautam. One question, or I was curious about. So you have all these observables, so to say, the searches, the weather. Well, maybe not the weather, but all these other characteristic searches from population, and then you also have these external factors like the weather and AQI. So, for example, when you wanted to look at distribution for diabetes, so in that case, are you able to look at the existing features and see which of these features are the biggest contributing factors in like some sense of yeah.
Yeah, that's a really good question. Like a lot of the people who use the embeddings, when they are applying some, or like when they ask a decision maker to like make some choice based on a prediction. Like oftentimes that'll be the main thing, like, oh, what is driving the signal here? So like we've broken up the embedding into like 3 different subcategories. And so then you can sort of get a sense like is search or maps driving this, but we can't, at least in the way we are providing the embeddings, we can't drill down into like this search query is driving performance. And part of that is us just making sure we're preserving privacy in these types of embeddings. But like the main thing I always think about is if there was like a single search query that was driving the performance through the graph neural network and the downstream model, that's like a really easy story. And you're like, oh, this is exactly what's happening. But like all of this machinery, I think, is picking up on signals that are really hard to explain. It might be like 150 different features that are driving performance. And then when you combine like, maybe it's like a popular search for like gardening equipment and like YouTube. And you're just like, this makes no sense. And I think that's actually like really important. That's the whole point, trying to pick up on these like important patterns that humans wouldn't intuitively understand. But I realized like when you're trying to explain it to someone, they were like, I just want a simple answer. Like, what is the one thing? And that's the trade-off here with interpretability and sort of complexity.
Or like, so I was not, I mean, for every different feature, like for example, maybe when you're looking at trying to model COVID outbreaks, and then it could so happen that your searches for symptoms for COVID are going up across the board just because it's like an external factor and everyone's searching about it. But then with people who are tending to show symptoms, so those are probably the people who are looking for remedies and possible medications. So so in that case, you might have a better indicator, or you might have these 2 very strong indicators where you're looking for symptoms and remedies, but the remedies is probably a stronger indicator to show tendencies of COVID outbreak cases, like not susceptibility, but infectiousness in the SIR model. So something like that. So would you be able to do this on a case-by-case basis? Like when I mentioned about trying to model toothbrushes in different zip codes.
I guess like you'd be able to understand, I guess, the dynamics of like COVID and zip codes, but drilling down into whether it was like people searching for remedies or like people just having symptoms. Like in this setup, we wouldn't be providing that interpretability.
Okay.
Yeah, it's supposed to be just like this like big soup of features that are able to help your downstream predictive model and try to like push the performance as high as possible. But like as far as like figuring out like what is driving it and everything in this very fine-grained manner, that's like I don't think that would be in scope, and mostly because of the privacy considerations there.
Oh, okay. Thank you. I had one other question, if there's any time. So, in the area where you use TimesFM or time series foundation model for a univariate time series, and try to use that to model the error or get geospatial relations. Instead of, or have you tried any other autoregressive models? You mentioned ARIMA, but just like a very simple time delay embedding of a longer time series.
Oh no, we have. Let me think. I don't think we have experimented much with the forecasting approaches, and maybe like parts of this is like reading into like when Google was doing the flu trends forecasting. I think maybe we're in some of it just looking at the previous time step is like an amazing. It performs extremely well for flu forecasting, and so I think the headroom is very low in being able to improve forecasting. It's like a very hard challenge problem. But yeah, there's probably like lots of research to try to like optimize this in some way.
No, thank you.
Yeah, you're welcome.
Awesome. So I think we're at like a little bit past time. So I think we're pretty set. I'm not sure if there's any other questions that are quick.
Yeah, maybe one question. I was interested when you said you were combining the PDFM outputs or like embeddings with the saclip embeddings. Was that just like sort of stacking them together and then into one like a larger embedding and then using that for downstream?
Yes, correct. Yeah, they was like stacking as opposed to adding it into the graph neural network. And maybe like I think I showed one plot where the performance in some instances was worse when we stacked them together. I'm assuming like if we had natively like put it into the graph neural network, we would have like optimized that better. And I'm like that dip wouldn't have happened because that didn't happen with the other modalities.
Interesting. Yeah, thanks.
Yeah. Well, thank you very much. Well, thank you. This was fascinating, Gautam. It's thank you for joining us.
Yeah, thanks for the opportunity. It was great to talk with you all.